So today in lesson 3, we're going to look at the normal distribution. Physical measurements such as length, volume, mass, time, they all tend to have a common distribution. So if I took the weight of infants, I would get a distribution scale where the majority of my infants have this average weight. Let's say it's 8 pounds. Then I have those that are on the low end of the scale, and then I have those big babies that are on the high end of the scale. The same thing, time to complete an assignment. You'll get kids in the class that complete the assignment very, very quickly, some that take a very long time, but the majority of students are going to be clustered around the middle. Or the heights of students in the class. The majority of your students are going to be clustered around this middle mark, but then you're going to have those students that are not as tall, and those students that are much taller than everybody else. Read. So if I was to draw or connect these points, what I would notice is I get a curve. What shape does this curve represent? What shape is that? It's a bell curve. Somebody reading ahead? Does it look like a bell?
That one does.
Do these not look like they could be bells if I put the little ringer underneath? Bells come in different shapes and sizes. It's called a bell curve. Bell curve, normal distribution curve, normal curve. It is used a lot for making predictions in statistics. If I can say that the data that I've collected for this example is distributed this way, I can then extend it to an entire population. So a good example, light bulbs. If I'm testing the lifespan of a light bulb, I can't test every light bulb because in order to test the lifespan of the light bulb, I have to actually burn up the light bulb. So I test a sample. And if I can determine that in my sample the data is distributed normally, I can extend that sample to the entire population. I can do the same thing when I'm coming up with warranties. So when you buy that toaster and it says it's got a 1-year warranty, it's because somebody has tested all of the toasters, figured out the normal distribution curve, and then figured out a warranty such that I don't have to replace a lot of toasters. So when you see a warranty or a guarantee on an item, somebody has tested it and has determined that you don't have a lot of replacement. They don't want to have to replace maybe more than barely 5% of their items. So extended warranty, be very careful of. Because again, the same thing. They figured out how much they're charging everybody for extended warranty. They're only replacing a certain percentage of items. So we're going to look at a manufacturer makes 100-watt light bulbs for Glow-Brite. What they did is they tested 44 light bulbs. And they determined that the mean life was 900 hours and the standard deviation was about 50 hours. So they created this histogram. There was one light bulb that lasted between 750 and 800 hours. That was this light bulb. Then I had 6 light bulbs that were between 800 and 850. That was these light bulbs in here. And then I had 850 to 900 and so on. So this histogram represents this information. So how many light bulbs were less than 800 hours? How many light bulbs is that? 1. How many light bulbs between 800 and 850?
6.
850 and 900. How many?
15.
And it's the same amount for the 900 to 950 because the bars were even. What about 950 50 to 1,000 hours? And more than 1,000 hours? So that was 44 light bulbs. If I calculate the percentage, they did this one for me. 15 out of 44 was 34.09. So what is 1 out of 44? To 2 decimal places. What percentage is that? That's not the percent, that's the decimal. Change it to a percent. Multiply by 100.
2.2%.
2 decimal places. 2 what?
7.
Okay. So that would be this percentage over here, because it's the same. And what about 6 out of 44? What percentage would that be? Thank you, Talia. And that would be the same as this one right here. So that's using the information from the histogram. If I change that histogram to my curve, or actually before I change it to my curve. So remember in the example, mu, or my mean, was 900, my standard deviation was 50. So if I had to write 950 in terms of these symbols, what can I do with 950 to get to 950? What operation?
Addition.
Pardon?
Addition.
Addition. So I can take mu and add 1 standard deviation. How would I get 850?
Subtraction.
How would I get 800? So how would I use 950 to get to 800? Subtract 2 of them. How would I get 1,050? Add 2, or how many would I add? 3. So if I complete the normal distribution curve based on the results from the last example. So this was that histogram that from the previous page. This was my 34.09. The other side was 34.09. We had the 2.27 here and here. And then we had the 13.64 was the remaining one. So those were my percentages. My data values went up by 50s or down by 50s when I'm working to the left. In terms of the number of standard deviations, the mean is 0 standard deviations above and below. This one is 1 standard deviation above, 2 standard deviations above, and 3. This is 1 below. How do I show that?
-1.
-1. 2 below, and 3 below. In terms of using the symbols, mu and sigma, not sigma, yeah, sigma. There's mu. There's mu plus 1 standard deviation, plus 2, plus 3. If I go the other way, I subtract. Now this was based on the data values. In reality, the figures for a standard normal distribution curve vary a little bit, and we'll outline that on the following page. So for population data with a mean of mu and a standard deviation of sigma, the normal curve is denoted by the points. Now this curve that is created has calculus behind it and how the curve is created. You don't need to know how the curve is created. You need to know what the properties of the curve are. So with the properties of the curve, the mean of the data set is at 0. In a standard normal distribution curve, we don't deal in actual averages and actual standard deviation. We make every mean equal to 0, and every standard deviation is 1 level. So the mean of the data becomes 0, and the standard deviation is 1. Now looking at this curve, how much or what percentage of the data lies above this curve? Well, what does this line do to the curve? Splits it in half. So if half is on this side, what's half as a percentage? 50%. And I could get 50% by adding these numbers together. 34.13%, 13.59%, 2.15%, and 0.13%. What percentage of the data is within 1 standard deviation of the mean? So 1 standard deviation, what percentage is that together? 34.13 and 34.13.
64. Yeah.
68.26, right? Okay, what about 2 standard deviations? So take this 68.26 and add on these two 13.59s. What do you get? Not 17. So I got 99.44 within 2 standard deviations, and then you said 99.74 within 3. This 0.13 and this 0.13 is not from 3 to 4. It's everything that extends indefinitely to the right and everything that extends indefinitely to the left. Because with that light bulb example, I had a mean of 900 hours. Okay? Well, what happens if one of the light bulbs that I picked burnt out within 100 hours? Well, 100 hours is going to be way over here in terms of the number of standard deviations. Or if I had that one light bulb that lasted for 1,500 hours, it's going to be way over here. So this 13 or 0.13% is those extreme outliers. And then we have what percentage of the data is between 1 and 2 standard deviations? 13.59. And that's between 1 and 2 above or 1 and 2 below. So we're going to look at the basic property of a standard normal distribution curve. Everything under the curve will add up to 1. All the percentages put together will add up to 100%. I already talked about how it extends indefinitely to the left and the right. So this line approaches the axis but never touches it. It's symmetrical amount, the mean, meaning 50% is on one half and 50% on the other half. All the data is represented by everything that's under the curve. So I'm not going to have a data value up here. They're all going to be underneath this curve. And the mean, median, and mode end up being the same value, which is right here. This represents the mean of the data, the median of the data, and the mode of the data. So a nurse records the number of hours a day an infant sleeps. Creates a normal distribution curve. What is the mean of this curve? Where's the middle?
12
What does that represent? 12 what?
hours slept.
So the baby sleeps on average 12 hours per day. What's the standard deviation? What am I going up by? 2. So the standard deviation becomes 2 hours. So with that knowledge, I want you to fill in what the values for A, B, C, and D are. So what are the values for A, B, C, and D? What's A?
6,
B,
8,
C,
16,
and D.
18.
So what are the percentage of days to the nearest hundredth does the infant sleep between 12 and 14 hours? So on my normal distribution curve, what percentage was within one standard deviation? Look on the previous page. 34 point, is it 13 or 09? Oh, sorry, 13. So 34.13 was right here, which is also right there. What did I have for a percentage within between 1 and 2 standard deviations? What was this percentage from the previous page? Pardon? And this one?
2.15.
So what percentage of the day does the infant sleep between 8 and 16 hours? So if I add all these together, that was within 2 standard deviations. You figured that out. 95.44%. What percentage of babies sleep for less than 6 hours a day? So if I have a baby that's sleeping less than 6 hours a day, should I be concerned? Yeah, because according to the statistics, less than 1% of babies sleep for less than 1 hour a day, or less than 6 hours. So if only like 0.1% of the babies sleep for less than 6 hours, and I have a baby that's sleeping for only 4 hours a day, I definitely should be concerned. Because babies aren't supposed to sleep just 4 hours a day. Likewise, if I have a baby that's sleeping 20 hours a day, I should be concerned for the same reason. Because again, less than 1%, like barely 0.1% of the populations of babies sleep for more than 20 hours a day. But everything else could be considered within that normal range. Can you tell me what percentage of babies sleep for less than 13 hours a day? Yes or no?
Wouldn't it be 34.13?
Where's 13?
Maybe a little bit more, 14.
But if I draw this up, does this split the 34.13 in half? Not really. So can I determine the percentage? No.
No.
Why not? Because it's in between standard deviations. There is a way of determining that, and that's what we're going to work through next. We probably won't get done the lesson today. We'll have to finish it tomorrow. To solve this, we use the concept of z-scores. So there has to be a way of determining percentages that are within the standard deviations. I can't just keep everything between 0 and 1, or 1 and 2, or -1 and -2. I have to be able to find those that are part way. So a z-score for a particular data value is the number of standard deviations the data is above or below the mean. So if I look quickly at this diagram, 13 is how many standard deviations above 12? This is one standard deviation. If 2 hours is one standard deviation, what's 1 hour? 0.5. So this would be 0.5 of a standard deviation above the mean. If I wanted to know about 9 hours, 9 hours is how many standard deviations away from 12? 1.5. And because it's below, it would be a -1.5. So if we look back at the previous class example, the data value of 18, and we have the nice chart below that we can look at. So 18 is 1, 2, 3 standard deviations above the mean. So it would have a z-score of 3. 8 is 2 standard deviations below the mean, which means its z-score would be -2. How many standard deviations is 12 away from the mean? Pardon? 0, because it is the mean. So it is no standard deviations away from the mean, so its z-score would be 0. And then 13, as we talked about before, is half a standard deviation above the mean. So the z-score would be 0.5, or 1/2. So if I look in terms of mu or in terms of the mean and the standard deviation, we did this already, where we said this was 1 standard deviation, 2, and 3, and then going backwards we subtracted. And then if we convert all of those to z-scores, there are my numbers. So with that information, how can I calculate a z-score for 13? Well, the z-score for 13 would be 0.5. But what if I wanted a z-score for 13.5 hours? 0.75. What if I wanted a z-score for for 11.3 hours? Starts to become a little bit more complex. Okay. That's why we have a formula. To calculate the z-score, we take the data value, so in our 13 example, 13 minus the average of 12 divided by the standard deviation of 2. So if I had if I had 11.3, it would be 11.3 minus 12 divided by 2. That would give me my z-score. When the z-score is positive, it tells me it lies above the mean. If the z-score is negative, it is below the mean. So I think I'm going to do one more part, and then we'll call it the end of this part. In this table, there's a rule that is sometimes referred to as the 68, 95, 99 rule. 68% of the data is within 1, 95 within 2, and approximately 99 within 3. So it's a good approximation. Approximately 68.3% of the data lies between a z-score of -1 and +1. 95.4% of the data would lie between a z-score of and 99.7% of the data lies between what two z-scores? So what I want you to do tonight is I actually want you to do questions 1 and 2. So do questions 1 and 2 first, and then we can continue on with the rest of the lesson. So to continue with lesson number 3 on the normal distribution, we're looking at using the z-score formulas. So the z-score formula is basically a way of telling me how many standard deviations above or below the mean I'm now at. So the heights in centimeters of 5 starting members of the Wolfhounds basketball team are 170, 182, 193, 195, and 210. If the mean height is 190 and the standard deviation is 15, calculate the z-score for the tallest player. The calculation for the z-score for the shortest player is shown. So x refers to the data value that you're given. Mu is the average of the data set, and then sigma is the standard deviation of the data set. So 170 minus 90, which is -20, divided by 15 gives me -1.33 to the nearest 100. If I look at the z-score for the tallest player, what was the height of the tallest player?
12.
So if I use this formula, the x value is 212, the mean is 190, and the standard deviation is 15. So if I go to put this into my calculator in one step, I want to make sure I have brackets here. So grab your calculators and tell me what that would equal. 212 minus 190 divided by 15. Yes, Matt?
I forgot my sweater in the other room. Can I go get it?
Yes.
Your batteries are what? Yeah. 199.222.
199? Did you divide? I would double check that. Pardon me?
1.46.
What's after the 6?
666.
So if I go to round this to 2 decimal places, the 6 would become a 7. So what it means is that the tallest player is just about 1.5 standard deviations above the average, whereas the shortest player is about 1.3 standard deviations below the average. Now, class example number 4 is an example of how z-scores can be used to compare your classes. So when you get your report card and your report card gives you your marks, and it says that you've got an 85 in math, but you've got like a 75 in physics, is your math mark really better than your physics mark? If I convert everything to z-scores, then I can come up with an accurate representation. Because if the class average and the standard deviation is such that in the physics class, my mark of 70 is actually much more standard deviations away from the mean than my math mark of 80, I might actually be performing better in physics than in the other class. these are Tony's midterm marks for the subjects, math, chem, and physics. So you've got Tony's mark, the class average, and then the standard deviation for each course. So if I calculate his Z-score for math, it would be his mark minus the mean divided by the standard deviation. So take your calculator and tell me what is 74 minus 68 divided by 4 or divided by 12.
What is this?
68.3.
Is this like
How much?
is this like
68.333.
Okay, try that again.
You have to put
But go bracket 74 minus 68 bracket divided by 12.
0.5.
Okay? I want you to do the same thing for his chem and his physics marks, please. So if we look at Tony's chem mark, the Z-score for chem would equal, so what would I write on the top for my formula? Divided by, and what does that equal?
0.425. 428.
So 425, so 43 then? Okay. Now his physics mark. Which equals
0.1817.
So looking at the Z-scores, which class is Tony actually performing better in? Math. This is his best class. Because in chemistry, he's half a standard deviation above the average. Whereas in chem and physics, he's less than half and he's only at like 2/10. So even though his math mark is lower than his chemistry mark, because of the class averages, it affects where he sits in the class. The class average in chem is higher than math, so his Z-score ends up being higher in math. So in class example number 5, 6, and 7, we look at solving for the other variables in the Z-score formula. So my Z-score formula is x minus mu divided by sigma. So the average mark on an English exam was 63 and the standard deviation was 12. The marks are normally distributed and a student's Z-score was 1.5. What did they actually get on the test? So if I go back through and I look at these numbers, 63 corresponds to which of these 4 variables?
what? That's not right.
12 corresponds to the thing on the bottom, we call it sigma. And 1.5 corresponds to the Z-score. So it's x that I don't know. So I want to get x by itself. So to get x by itself, the first thing I want to do is get rid of this 12. How do I get rid of the 12? Multiply both sides by 12. So what is 1.5 times 12? What'd you get, Courtney? 18, thank you.
48.
How do I get rid of the 63?
Yes.
So what is 63 plus 18?
But did you
How
use
much?
the right answer?
81.
So the actual mark was 81. Okay, the next question. So again, I start off with my formula. Z equals x minus mu divided by sigma. The weights of a large shipment of cantaloupe are normally distributed with a mean of 2.3 kilograms. The weight of a particular cantaloupe is 1.7 kilograms, which is 1.01 standard deviations below the mean weight. Determine the standard deviation to the nearest hundred. What's X? What's the value of X in this question? Pardon? In this question? In the cantaloupes, what's X?
Would it be 2.2 kilograms?
What does 2.3 tell you? What does it say about 2.3?
Oh, with the mean.
So 2.3 would actually be the mu.
No, but like this one.
What's X?
1.7.
Standard deviation is what I'm asked to calculate. What's my Z-score?
Is that what we're trying to figure out?
No, I'm asked to figure out the standard deviation.
Yeah. So it's 1.01.
What words in the question tell you that that's the Z-score? Because it doesn't actually say the Z-score is 1.01. What does it say? It says it's 1.01 standard deviations below the mean weight. Remember, Z-score tells me how many standard deviations I am away from the mean. Now, if I'm below the mean, what should my Z-score actually be? How do I know if a Z-score is above the mean or below the mean? Because one standard deviation could be above or it could be below. What do I use to differentiate between the ones that are above and the ones that are below? So the word below the mean weight means that my Z-score has to be a negative 1.01. If sigma is on the bottom, I need to bring it to the top. So to do that, I multiply both sides by this sigma. So I will get negative 1.01 sigmas equals, what's 1.7 minus 2.3?
Negative 0.6.
6, sorry. How do I get rid of the negative 1.01 on this side so I'm left with just sigma? So negative 0.6 divided by negative 1.01 would equal 0.59. What's after the 9?
4.
So to the nearest hundredth, 0.59. That becomes my standard deviation. Now your standard deviation is always going to be a positive value. Standard deviation talks about the disbursement of the data around the mean, and it does not look at it as being a positive or a negative value. Okay, the last question. The marks on a math exam at a university are found to have a mean of 52 and a standard deviation of 12. So that means within one standard deviation, which was 68% of my data, that chart, or that curve that said it was 68, 95, 99, that means 68% of the marks in my class were anywhere between 40% and 64%. Professor thought that maybe this exam was a little too difficult, so he adjusted the original marks. He changed the mean to a 65 and then reduced the standard deviation to a 10 and left the Z-scores unchanged, and then used the Z-scores to calculate the new course or the new exam mark. So what would the new mark be if the original mark was a 34? So the first step is I need to find out what the z-score of a mark of 34 was on the original exam. So that's my x minus mu divided by sigma. So I'm going to give you a moment, and I want you to use the original marks, the original mean, the original standard deviation to determine the original z-score. So how did you calculate this?
34 minus 62 divided by 12.
And what do you get?
Negative 1.5.
So that becomes the z-score for my new mark. So my new mark, which is x, the z-score remained unchanged. So the z-score becomes the z-score in my new calculation. The mean was changed to a 65, and the standard deviation was changed to a 10. See if you can solve that equation for me. So what's the first thing that you would do to solve for x?
You gotta bring the 10 up.
Okay?
Then equals negative 50. Then you gotta add 65 together. Get everybody's off. And then you get 50.
So he now has a mark of 50% instead of a mark of 34. This is done. And it's not even just necessarily done at a university. Marks can be adjusted using this type of method. So I kind of keep everybody's z-score or the distance away from the mean the same. So I'm not necessarily elevating everybody's mark by 10%. I'm taking into consideration where they are in relation to the average set. So the questions that I want you to work on are these ones. 4, 5, 6, and 7, practice solving for the various variables within the formula. And then 10 to 12 are some problem solving.
Yeah, exactly.